Now we're on to part 2 of solving a magnetic circuits problem. In this video I'm going to be showing you how to solve the operating point of a magnetic circuit graphically and also analytically. In a general case where we have a nonlinear ferromagnetic material for our core, where we have a BH curve that's nonlinear. Okay, here we have our magnetic circuit. We have a core material and then we have an air gap. We have the length of the gap Lg and then the length of the core is Lc. Now we'll have a flux in the core and we'll have a flux in the gap. Well, in a series magnetic circuit, it's a flux that's continuous across the boundary. So the flux in the gap is going to equal the flux in the core. When we have these two values equal, then we will have solved for the proper operating point of the circuit. Now, because of the nonlinear nature, we didn't have a good analytical way of solving this like we did initially when we assumed and was given the permeability of the core material. In general, we don't know what that permeability value is because it varies with the strength of the magnetic flux intensity in the core. So we wind a coil around the core as before. We have 130 turns, or N, the number of turns in the core or around the core. N is 130, and we have a 15 amp current flowing in the coil. So the magnetomotive force is our ampere-turns, which is 130 times 15 or 1950 ampere-turns. Now, to find the operating point on the BH curve, the BH curve is for the core material, so I'll call this H of C and B of C. The B is given in Teslas, the H is given in ampere-turns per meter. And we have this nonlinear characteristic. And again, the flux is continuous throughout the magnetic circuit. The BH curve characterizes the magnetic field conditions inside the core, not in the gap, but in the core. We have to modify our BH curve here, scale, to represent the flux in the core versus HC, because it's the fluxes that we need to equate between the gap and the core, not the B fields in general. It happens before that we could equate the B fields because we had assumed that the area of the core equaled the area in gap. In general, that's not going to be true. So I'm going to solve this the way you would as if the areas in the gap and the core were not the same. So we need to equate the fluxes. So we need to change the scale, the vertical scale, to represent Webers, or the flux in the core, rather than the B field in the core. Now, once we have the flux in the core versus the H field in the core, rather than the B field versus H, which the BH curve represents, we can then plot on this graph, once we have flux versus the H field in the core, we can plot the flux of the gap, the flux in the gap, as the H changes. And where the two curves intersect will be our operating point. Then, once we find where on this curve the circuit is operating, we can read off the B field and the flux in the core, and then the flux in the core will equal that in the gap, and we can compute the B field in the gap by dividing the flux by the area of the gap. So first, we have to change the scale of the core material, and the way we do that is we know that the flux in the core is the area of the core times the B in the core. So what we do is we multiply this scale by the area of the core, the cross-sectional area of the core, to change the scale. So here we'll have our flux values. They just differ by the B field in the BH curve by the area of the core, whatever the area of the core is. So once we have the scale, the vertical scale changed, then we need to determine an expression for the flux in the gap as a function of the H field in the core. So as the H varies in the core, the flux in the gap is going to change. And we need to find an expression for that. And the way we do that is we start with Ampere's law. We have Ni is equal to the H in the core times the length of the core plus H in the gap times the length of the gap. Let's solve for Hg. That is the H field in the gap. H field in the gap will be Ni minus HClc divided by the length of the gap. Now, the flux in the gap is the area of the gap times the B field in the gap. But what is the B field? The B field in the gap is related to the H field through mu zero. We are dealing with air in the gap, so remember B is equal to mu H, but in the gap our mu is the free space value, mu zero. So then we can write this as A area of the gap times mu zero times H of the gap. Now, we substitute in our H in the gap from Ampere's law into this expression. So we've got area of the gap times mu zero times this quantity, Ni minus HC LC divided by the length of the gap. Now, let's multiply this out. We got phi in the gap is equal to Ag mu zero Ni over the length of the gap minus Ag mu zero over length of the gap times LC HC. Now, what is this? This is an equation for a straight line. This is an offset, mu zero. This is the slope, call it M, times HC. So we got the flux in the gap is equal to an offset, mu zero minus MHC. Well, our mu zero, the offset is A G mu zero, area of the gap times mu zero divided by LG times the ampere turns, and our M is area of the gap times mu zero over LG times LC. I partitioned it this way because in parentheses we have the same value, so we only have to calculate it once in that case. So this is the equation of a straight line with a negative slope with respect to phi, our flux, and the H field in the core. So it's going to be a line with a negative slope when we plot the flux in the gap versus the H field in the core. So where these two intersect, that's going to be our operating point. It's unique. There's only one value. So that's graphically how we will solve this magnetic circuit. All right, let's put in our values and see what we have. This, again, is the BH curve. This is for our core. This is the curve for the core, and the straight line is for the gap. and where they meet is the operating point. So let's look at the problem using our 2.5 millimeter gap. Okay, so we're going to assume the length of the gap is 2.5 millimeters, or 0.0025 meters. Okay, let's calculate our offset, our phi 0. Remember here is that the flux in the gap is our offset phi 0 minus m h of c. So, phi 0 is this value. The area of the gap, these, remember, are 5 times 10 to the minus 4th square meters. So we've got 5 times 10 to the minus 4th times mu 0, which is 4 pi 10 to the minus 7th, over the length of the gap, which in this case is 0.0025, and then ampere turns, we have 1950. Well, that value comes out to 4.901 times 10 to the minus 4th Webers. That's the flux, offset flux. How about m, the slope? M will be this value here. I'll just write that like that. That is this value times the length of the core. Well, the length of the core in this case, remember, was from before 0.50015 meters. And this value comes out to 1.257 times 10 to the minus 7th Henry meters. That's the value of m. The units on our slope is Henry meters. Now, okay, so our line now has the equation phi in the gap is equal to 4.901 times 10 to the minus 4th minus 1.257 times 10 to the minus 7th HC. Well, to plot our straight line, the best thing to do is first make HC 0. So when HC is 0, our value for the flux in the gap is 4.901 times 10 to the minus 4th. So if I go over on the graph here, when H is 0, we have, I'm putting my point here, I've converted my B field, BC, into Webers here by multiplying BC by the area of the core. And if I find this line here is 5.0, I want 4.9, so I'm a little bit below that at 4.9. That's the first point on the line. Now, we can pick a value for HC. Let's go as far out as we can. Let's just pick an HC of 500. So, when HC is 0, our flux in the gap is 4.901 times 10 to the minus 4th. And when HC is 500, our flux in the gap is 4.275 times 10 to the minus 4th Webers. So at 500, I plot a point. This line here is 4. so 4.275. This is 4.5 here, so 4.275. So I draw a straight line between the two endpoints on the line. The intersection point is our operating point. And if I read off the graph, I see that the B field in the core, this is 0.9 here, so it's 0.91, and the corresponding H field in the core is right around 290, just like we had before. So this is graphically how we solve the problem. So in this case, our HC is 290 ampere turns per meter, and our BC, which we read off the graph, is 0.91 Tesla, just like we had before. So that's graphically how you can solve the network. Is again, the phi 0 represents an offset. The m is the slope of the line. We put in a couple values for HC to get points on the lines. 2 points define a line. And then we draw our line, and where it intersects with the BH curve for the core, that's our operating point. Now, I'm going to show you a way to solve this nonlinear problem analytically. To solve the general problem analytically, it falls upon us to try to find an expression that relates the B field in the core to the H field in the core. Remember, that relationship is nonlinear, so we need to come up with a nonlinear equation for expressing B as a function of H in the core. The problem that we have, again, is we have this core material, and we have a gap where LG is the length of the gap, and the mean radius of this C of the core is cap R. Now, we've assumed all along here that the area, cross-sectional area of the gap and the core are the same at 5 times 10 to the minus 4th square meters, or 5 square centimeters. And the radius of the mean radius of the core is 8 centimeters. Well, I'm not going to show you how I derived the analytical expression. That's for another lecture. I'm very good at curve fitting. I can look at graphs, and I'm pretty good at figuring out what is the functional relationship that would help me fit the curve with some analytical expressions. Well, if you look at our curve, this is our BH curve, the nonlinear curve. It looks like an offset hyperbolic tangent function. A hyperbolic tangent function, if you remember, looks something like this. So if I offset the hyperbolic tangent function so that this part starts around 0, it's going to look something like this, and then you have to add in some offsets to both the x and the y coordinates and a scale factor to make the curve fit. And I was able to get a very good fit in about 10 minutes of playing with a hyperbolic tangent function. So this is what I came up with. The B in the core versus the H in the core is this expression, 0.66 times the quantity hyperbolic tangent, the H in the core divided by 125 minus 1.96, then to that hyperbolic tangent function you add 0.097, and then multiply by 0.66. And it very well fits this curve that I have here, this BH curve. So this is in Webers per square meter, where the H in the core is ampere-turns per meter. Now, remember from before in the air gap, we had this expression for the air gap. The flux in the gap is some offset, phi 0, minus a slope factor, m times h of c, where phi 0 is given by this expression, and the slope is given by this expression. I'm keeping it so far in general. I haven't made any substitutions for the gap area or the core area. Now, the key here is that the flux is going to be continuous across the core gap boundary. That is, we have a flux in the core. It comes through, it comes to the boundary, and it goes across in the air gap. Well, the flux in the core here is going to equal the amount of flux in the air gap for a series magnetic circuit. That's the key point. So I equate the flux in the gap to the flux in the core. Well, the flux in the core is related to the B field in the core by the area of the core. So if I multiply the B by the area in the core, I get the flux in the core. So here we have the core area, cross-sectional area, and here we have the gap cross-sectional area. So relating this is I equate the flux in the gap to the flux in the core. Here's our flux in the gap, phi0 minus m hc, and I've multiplied AC through here, so I've got 0.66 AC times the hyperbolic tangent of this, plus 0.97 times 0.66, which is 0.6402, times the area in the core is equal to the flux in the gap. Putting everything on one side, moving everything over to the left-hand side, I define a variable y prime is 0.066 area of the core times the hyperbolic tangent plus mh of c plus 0.6402 area in the core minus flux 0. Now, this is just a constant. That's an offset. That does not involve h of c. So we have a hyperbolic tangent function involving h of c, and we have a linear term involving h of c. Now, if I put in the value, equate the gap area, cross-sectional area, to the core cross-sectional area, which is 5 times 10 to the minus 4th. So we put that in here and here, and I multiply by 10 to the 7th. So I define a new variable. Y is y prime times 10 to the 7th. That's to get rid of a lot of the negative exponents. So this is the expression after I substitute in for the area in the core, 5 times 10 to the minus 4th in this expression. And this is what we get right here. So I now have an expression for h of c, the h field in the core, that the value of h of c that satisfies this equation, that is, makes this equation vanish, goes to 0, is the operating point. That value of h of c that will make the flux in the gap equal the flux in the core. Now, I've done this in general. All I've done is assumed that the gap area, cross-sectional area, and the core cross-sectional area are equal at this value, but I have not put in a value for the gap width. We will solve this equation, express it as a function of the gap length, the gap length, so we can solve the problem as a function of LG and see how the operating point changes as we increase the gap length. Now what I'm going to do is we have y equal to this. I'm going to call this a function f of hc to make it simplified, because this is only a function of hc and not the gap length. The gap length appears in the m here and in phi 0, but not in here. So I can write this now as the following equation. I will write this as y is equal to F of HC plus M times 10 to the 7th HC plus 3201 minus 10 to the 7th phi 0. And we want to find those values of HC that makes that 0. Now, watch what happens here. Is the operating point now will be a function of the gap. We're finding those values of HC that make this equation go to 0 when we put in a certain value for the gap. Again, the M value is the gap area times mu 0 over the length of the gap times the length of the core, and our phi 0 is the gap area times mu 0 over the length of the gap times the ampere-turns, the magnetomotive force that drives this coil, or drives this circle. We have N terms and we have a current I, so N times I is our magnetomotive force here. Now, I'm going to build a table. Here we have our gap length in millimeters. This is phi 0 times 10 to the minus 4th. This is my M times 10 to the minus 7th. And here is our equation. Then our HC and our BC, the H and the B in the core. All right, for 2.5 millimeter gap opening, our phi 0 is 4.901. So when I put a length LG of 2 millimeters in here, or 0.0025 for the gap length, then the phi 0 computes to this. The M, given the core length from this, where our R is 8 centimeters, the mean core length is 2 pi R minus the gap length. And that is our LC here. When I put in for there, my M in this case is 1.2570. And then the equation is F of HC plus 1.257 HC minus 1700 equals 0. Okay, for a gap of 5 millimeters, this is 2.450. This is 0.6254. This is F of HC plus 0.6254 HC plus 751 is equal to 0. For 7.5 millimeter gap, this is 1.634, 0.4148. The equation is F of HC plus 0.4148 HC plus 767 equals 0. And lastly, for a 10 millimeter gap, we have 1.225, 0.3095, F of HC plus 0.3095 HC plus 1976 equals 0. Now, these equations, these part don't change as I change the gap, because our f of hc, remember, is 3,300 times the hyperbolic tangent of hc over 125 minus 1.96. That's the same for all four equations. That's our f of h. Now, to solve these equations, as I vary the gap, I used Wolfram alpha, and I just put these into the function solver in Wolfram alpha. This is highly nonlinear. You have to use some numerical methods to solve this. So, for example, for the 10 millimeter, what I typed into Wolfram alpha is f of hc, which is 3,300 hyperbolic tangent of, I used x instead of hc to make it easier to type in. The values of x that solve this equation will be the hc. So here's the f of hc part, and then I add to that 0.3095 x plus 1976 equals 0. Put that into the equation solver in Wolfram alpha. Here is the example of the printout that I got. And you can see, here's the equation, 3,300 hyperbolic tangent x over 125 minus 1.96 plus 0.3095x plus 1976 equals 0. And then let it solve. And it gives you a graph. And the root plot is, there's the root of the equation. And all you have to do is move your cursor over there, and it gives you the xy coordinates. The x coordinate in this case is x is 156. So for this particular equation, our h is 156 ampere-turns per meter. That's the x value that satisfies the equation given by Wolfram alpha. So this is the HC, and here's the BC. Now, to get the value of the flux density, you have to take the HC that Wolfram alpha gives you and go back to the original equation that I had for on the curve fitting that I had. And that is right here. Now, that is the equation that I came up with, and I plotted it using Wolfram alpha. And you can see that it looks just like the curve that I started with, the BH curve. So what we do then is, once we have the value for HC using the equation solver and Wolfram alpha, then we take that value of HC and just plug it into this equation. It turns out that you can just do this in Google. You don't have to use Wolfram alpha. If you just say take HC 156, so if I write that y equals 0.66, or I just type in 0.66 times hyperbolic tangent of 156 over 125 minus 1.96 plus 0.97, Google gives you the value. So once you get the HC value, you can easily, using the equation that I derived, get the value for the B field in the core. So, again, to recap, is we just use the equation here, use Wolfram alpha to find the root. You get the value of HC. Then you plug it in to the equation I derived, the value of HC, which is, to get BC, it is 0.66 times the hyperbolic tangent of HC over 125 minus 1.96 plus let's see, hyperbolic tangent of that. Got a mess here. Let's redo this. So this is 0.66 times the hyperbolic tangent of HC over 125 minus 1.96 plus 0.97. So you use this in Wolfram alpha to find the value of x, or the HC, that satisfies the equation. Then you go back to the equation that I derived for B as a function of HC to get the BC value. So once we do that, you'll find that it's 0.236 for, if I use this equation here for a 7.5 millimeter gap. These are the values. For the 0.5 millimeter gap, here are the values. And for the 2.5 millimeter gap. And you see that they agree with both the analytical method and the graphical method and the iterative method. We solved this one several ways, and we're getting values that are very close. And here are for additional gap widths. Now, if we plot this out, we can see how the operating point changes with gap, with the gap width that changes. Now we can see how our operating point changes as we change the gap width, or the gap length. Here is for a gap of 2.5 millimeters, and here's our operating point. We have a B field in the core of about 0.91 Webers per square meter. And if we double the gap width to 5 millimeters, the operating point drops down here about half. We're in the linear region. It drops to about half of what it was with a narrower gap. And then as we continue increasing the gap length, or the gap width, our operating point moves downward. We have our field intensity decreases, as we would expect it to, as we increase the gap width. Now, here are some points. Here are the values for the length of the gap and the H in the core and the B field in the core. And we can see that it is not a linear relationship in the core. If I double the gap, the H just drops some, and if I double it again from 5 to 10, it drops about 50% or 25%. It doesn't go as a linear relationship in the core, but in the air gap it does, as we might expect it to, because remember, most of the ampere-turns are dropped in the core, or in the gap, So we would expect a linear relationship in our H or in the B field as we change the gap length. So doubling from 2.5 to 5, we can see that the B field drops by about half. And if we double again from 5 to 10, it again drops by about half, from 0.46 to 0.23. That's because most of the ampere turns, the magnetomotive force, is dropped in the air gap, and the relationship between gap length and the B field will be linearly related because of the linear relationship between the H field and the B field due to the permittivity of the air in the gap. So for grins, I went ahead and I solved the problem graphically as well as analytically here. And you can see how similar the operating points come out. Here I solved graphically as before. Here are the load lines of the air gap plotted, and where it intersects the BH curve are the operating points. And here are the values that I got for mu0 and m as computed here. And here is plotted on the BH curve the operating points calculated analytically using this nonlinear equation, and we can see that they're agreeing quite accurately with one another. Here we're at a little over 150, and we're reading a little bit about 2.5 there. If we're a little bit to the right of 150, we're at about 2.5 on there. So we see that they agree quite accurately, whether you solve it graphically or manage to figure out an equation for the H field in the core, how it's related to the B field. So that pretty much ends all the solving the equations and how you would solve a magnetic circuits problem. To recap, we have several different ways. We can do it analytically if you can manage to come up with an expression for the magnetic flux density as a function of the magnetic field intensity in the core material. You can solve it graphically, where you have the BH curve and you put the flux equation for the air gap plotted on the same graph, and the intersection points give you the operating point. And then the other way is using the BH curve and solving it iteratively, taking a guess at how much of the ampere turns are allocated to the core and how many are allocated to the gap, and then compute the flux both in the core and the gap and compare them. If they're the same, you're done. If they're not the same, you adjust the value of ampere turns that you allocate to the core versus the gap, and you recompute, look at the fluxes, and if they're not the same, then you readjust your values of ampere turns, allocations between the gap and the core. keep doing this iteratively, and hopefully with proper guesses you will converge to the operating point. So That's how you solve magnetic circuits problems. Now, in the future, sometime in the future, I'll do some magnetic circuit problems that are much more complicated than this, but the procedure is the same. For example, to solve, you can have the equivalent of a series parallel network, just like you do in electrical networks. Here we have a more complicated core material, and we have two air gaps. And what we would do is wind a coil around the center, put a current in it. We have N turns, and there's our current that establishes our magnetomotive force that activates this network. Multiply N times I. Now, what you have to do in using an iterative scheme is you have a flux that comes up and divides. Some of the flux goes this way, some of the flux goes this way, jumps the gap, comes back, jumps the gap, and comes back. And to add more complications, you could have different areas. You could have a gap area A1 there, a gap area A2 there. You could have a core cross-sectional area of, say, A core here, and you could have a different area, A core 1 there. You could have a different core area there. But even if it's this much more complicated, you build yourself a table, and what you do is you take guesses of how many ampere-turns are allocated to this and this portion of the core. Say this portion of the core, that and that would be the same. And then an allocation for this portion of the core, and then in the center. So the flux in the center, you essentially have a parallel circuit here. You've got electrically, what this would look like is you'd have a voltage source, a resistance, and then there's a resistance here in the core, a resistance in the gap, and then another resistance in the core here, and then coming this way you have a resistance in the core. Let's call this 1, let's call this 2. Resistance in the gap 2, and then more in the core here, resistance in the core 2. This would be resistance in the core 1. And then a resistance here in the center leg. So you have a series parallel network, and it's the same thing with the magnetic circuit. And what's important here is the Ampere law equation, that Ni equals the ampere turns in various parts of the leg must all sum up to the driving magnetomotive force. And you'll end up with several equations, because you'll have an equation for the center leg and then another equation on the right and the left side. But nothing's changed. It's just a little more in terms of housekeeping and bookkeeping on the values. But the important thing is that the flux, you have to keep in mind the flux remains constant or continuous going across this boundary between this core and this air gap, and the same thing here. So in this portion of the network, the flux is all the same, then it divides, and we'd have, say, a phi1 going this way, a phi2 going this way, and then a phi called phi primed in the center portion. So phi primed is going to be equal to phi 1 plus phi 2. So you can have all kinds of complicated magnetic networks, but you use the same procedures. You just have to do more bookkeeping in order to solve a more complicated magnetic circuit like this. So hope that helps. It's been a long drawn out thing, but I wanted to show you all the different techniques that you can use for solving magnetic circuits, and hopefully if you're interested in this sort of thing, you just need to practice.